Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrunner, and today I'm going to show you how to do radix conversions with an emphasis on binary, octal, and hexadecimal. I'm going to teach you the easy way and some of the other ways you might need to know. Today we're going to talk about different radix number systems, and we're going to focus on radix 2, 8, and 16. That's binary, octal, and hexadecimal. We will consider number systems where we have radices greater than 1 that are integers. And we can talk about then the most typical digit set, which will go from 0 to r minus 1. So for decimal, which is base or radix 10, we have digit set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have exactly 10 different digit symbols. And in general, you will have exactly r different digit symbols. We can write, for this kind of positional notation, we can write any number as the sum of all the digits over all the digits of the digit times the radix to the power I. So for digit 0, we'll have the digit 0 times r to the 0, which is 1. So that will be the ones place. This is just a compact notation that is useful when we write digits. So binary, or radix 2, is the most common use. This is what's used in modern computers. The digit set is going to be 0 up to r minus 1. Since r is 2, the digits are only the set 0, 1. Okay, octal came about as an easy way to visualize binary, and we'll talk about that later. But in octal, the digit set goes from 0 to r minus 1. Since r is 8, we go 0, 1, 2, 3, 4, 5, 6, 7. Each of these octal digits will represent exactly 3 bits. Hexadecimal is most commonly used now for visualizing binary values, and it's often called just plain old hex. The digit set is going to be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, 15. Instead of coming up with new symbols to represent 10, 11, 12, 13, 14, 15, people just use the capital letters on the keyboard. Okay, so A is 10, B is 11, all the way up to 15. You should go ahead and make sure that you have those in your head, and we can talk about that more in a later video. But just go ahead and look at those and remember them. Each of the hex digits is going to represent a sequence of exactly 4 bits. We can have a table, and I've just split my table up because I didn't have much space, right? So we can write a table where we take the numbers in base 10 from 0 up to 15, write the equivalent values in base 2, base 8, and base 16. So what we find is that for base 10 in binary, 0 is the same as 0, 1 is the same as 1, but now 2 we're going to represent as 1, 0. Okay, that's 0 times 2 to the 0 plus 1 times 2 to the 2. And then 3 is 2 to the 1 plus 2 to the 0. So you can think of this as counting 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, up to 1, 1, 1, 1. And then the next number would be 1, 0, 0, 0, 0. Similarly, we can write base 8, which is octal. 0, 1, 2, 3, 4, 5, 6, 7 is going to be the same as the decimal. But now 8 is going to be represented as 1, 0. That's 8. That's 1 times 8 to the 1 plus 0 times 8 to the 0. So we think about counting 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. The next number would be 2, 0. Okay. Similarly, hexadecimal, radix 16, goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, which is 10, B, 11, C, 12, D, 13, E, 14, F, 15. The next number then would be 1, 0. We can do arithmetic in different radices. We'll talk about that maybe another time. Powers of 2 that you should know is from power of 2 to the 0 up to 2 to the 10th. I've written out some more for you. I find those are the easiest to, worthwhile to remember those. Anything bigger, if I need to compute, I just compute it. It's not that hard. Powers of 8, I try to remember up to 512, 1, 8, 64, 512. Powers of 16, it's nice to remember from bigger powers, depending on what you do in your job or in your daily activities, it's sometimes to know like what a meg is. But I find that just knowing 116, 256, 4096 gets me through most of it. And after that, I can use a calculator. Now let's talk about converting between different radices. So if we have numbers in one radix and we want to convert it into the other radix, we have several techniques we can use. First of all, there's a shortcut that if you're converting from a base that's 1 power to of a number, like octal is 2 to the 3rd, to hexadecimal, which is 2 to the 4th, you can go through binary as an intermediary, and it will work very well. Just as a side comment, if you were going from base 9 to base 27, you could also go directly through base 3 in the middle. Okay, but really going from octal to binary to hexadecimal, those are the useful ones. And I'll show you a quick technique to do that. Otherwise, you want to maybe try to make sure you're doing all your arithmetic in base 10. It makes life a lot simpler. So if your new base you're converting to is base 10, so you're converting from any radix into decimal, you can either use direct evaluation or Horner's method. I find direct evaluation is usually the easiest, but I'll show you both of those. If you're converting from radix 10 into another radix, then the easiest thing to do would be what I call guessing. You can also use a technique called repeated division, and I'll show you both of those. So let's start off with looking at substitution of digits. Suppose we want to convert the number 3F6 from hexadecimal to octal. Well, this is one of those cases where 16 is equal to 2 to the 4th and 8 is equal to 2 to the 3rd. So the simple thing to do is to go from base 16 to base 2 and then to base 8. So let me show you how to do that. We would first convert each digit into binary. I like to start where the hexadecimal point would be. Okay, and so 6 corresponds to the hexadecimal digit 0110. F is the hexadecimal digit 1111, and 3 is the hexadecimal digit 0011. So what I have done is I have used my quick knowledge of the binary equivalents of the hex digits, and just wrote them out. This works because 4 bits exactly represents hexadecimal digits. Then we would again start at where the binary point is this time, wherever the radix point is, and we're going to group our number in groups of 3 because octal is 2 to the 3rd, 8 is 2 to the 3rd, and we will just group in groups of 3. At the end, it came out even. That's not always the case. If you need extra digits over here to make a group of 3, just add on zeros, and it will change the number, so it will work. Now then, we convert. 110 is 6. I have another 110, that's 6. 111 is 7. And 001 is 1, and that's the answer in octal. Okay, now let's look at direct evaluation. Suppose you're given this number in binary, and we want to convert it to base 10. What we do is we start at the binary point, which is right here, just to the right of the least significant bit, and we multiply. We just use the polynomial expansion. So we'll have that least significant bit is 1 times 2 to the 0. The next digit over is 1 times 2 to the 1. Then we have 0 times 2 squared plus 1 times 2 to the 3rd plus 0 times 2 to the 4th. 1 times 2 to the 5th, plus 1 times 2 to the 6th plus 0 times 2 to the 7th plus 1 times 2 to the 8th. And that is going to be then simplified to, so we have 1 times 1 is 1, plus 1 times 2 is 2. 0 times 2 squared is 0. 1 times 2 cubed is 8. 0 times 2 to the 4th is 0. 1 times 2 to the 5th is going to be 1 times 32. 1 times 2 to the 6th is 1 times 64. 0 times 2 to the 7th is 0, and 1 times 2 to the 8th is 256. When we add these values up, we end up with 363 base 10. We can do conversion from base 16 to base 10 in the same way. We will start again at the binary point, the hexadecimal point. We'll have 6 times 16 to the 0 plus 9 times 16 to the 1 plus D is 13. So we'll have 13 times 16 squared plus 3 times 16 cubed. And then we can again multiply this out. That gives us 6 times 1 plus 9 times 16 plus 13 times 256 plus 3 times 4096. And when we multiply that out and add, we end up with 766 base 10. And I did use a calculator to add those up. These are not something that you couldn't do by hand if you had to. Now let's look at Horner's method. And I will just let's start with converting base 16 into base 10 first. It actually is a little easier. So we'll start off again. So the way Horner's method works is we're going to start with the most significant digit, so in this case 3, multiply it by the radix, 16, add the next digit, which is D, which is 13, multiply that by 16, add the next digit, which is 9, multiply by 16, and add 6. And you will get the same answer we got before. And that answer is, just so you have it handy, is 15,766 base 10. Okay, but I want to point out to you an easy way to look at this. So if we look at the most significant digit 3, and we look at how many times it gets multiplied by 16, we see that we can reorganize this computation. So it's 3 times 16, let's see how many times, 1, 2, 3. 3 times, 16 cubed. And then 13 gets multiplied by 16 twice. And then 9 only gets multiplied by 16 once. And then 6 is never even multiplied by 16. And so this just shows you, this is a different way of organizing the computation that we did with our direct evaluation. This is particularly useful for sometimes if you wanted to write an algorithm so that a microprocessor would be doing the computation or the conversion. Okay, we can write the same thing for the binary. I'm not going to do the whole thing because it gets really messy. But again, you would start with the most significant digit, multiply it by 2, add the next digit, multiply that by 2, add the next digit, multiply that by 2. It's hard to keep track of where you are. But add the next digit, multiply by 2, etc., till you add the last one. Okay? And again, you will come up with the number 363 base 10. And if you go home and multiply this out and write this all out, you'll see that this most significant digit here, this 1, is multiplied by 2 8 times. Okay, so that's Horner's method. It's sometimes useful. I just want you to know that it exists. We will almost always in this class use it. I think we will always use direct evaluation. Okay, if we want to convert from some decimal value into another radix. The easiest way to do that is called a repeated division, and I can walk you through how that works. We take our decimal number divided by 16, and I happen to have the answers to the left of me here. So 16 goes into 15,766 985 times with a remainder of 6. And then we do 16 goes into 985 61 times with a remainder of 9. And 16 goes into 61 3 times with a remainder. 16 goes into 61 3 times with a remainder of 13. And then 16 goes into 3 0 times with a remainder of 3. We read from the bottom up, and we will then get 13 we write as D, so 3D96 base 16. And that's how that works. I wrote the answer down here just so I can make sure that I got it right. Okay, now let's do the same thing with binary. We take 363, divide by 2. We divide by 2. I'm doing this in my head. We get 181 with a remainder of 1. 2 goes into 181 90 times with a remainder of 1. 2 goes into 90 45 times with a remainder of 0. 2 goes into 45 22 times with a remainder of 1. 2 goes into 22 11 times with a remainder of 0. 2 goes into 11 5 times with a remainder of 1. 2 goes into 5 2 times with a remainder of 1, and 2 goes into 2 1 time with a remainder of 0, and finally 2 goes into 1 0 times with a remainder of 1, and we read going up, and we get 1 0 1 1 0 1 0 1 1 in binary, and that's the conversion. So repeated division works pretty well. I find that the guessing is easier for me, but you can be your own judge there. Now let's convert 363 to base 10 to binary by guessing. So I could write over here my powers of 2. 2 to the 8th is 256. 2 to the 7th is 128, etc. I'm just going to keep them in my head, but you might want to, on your piece of paper, write them down. 363 is less than 512 and more than 256. So I'm going to subtract off the 256, which is equal to 2 to the 8th. I make a note. Do the subtraction. I get 107. 107 is less than 2 to the 7th, and it's bigger than 2 to the 6th, which is 64. Do the subtraction, and I get 43. 43 is bigger than 32 and less than 64, so I subtract off 32, which is equal to 2 to the 5th, and I get 11. 11 is less than 16, and it's bigger than 8, and I get 3. 3 is actually equal to 2 to the 1 plus 2 to the 0. I could have done the subtraction, but when I get down to something that's easy to write, I usually just write it down. Now I can write that as a number. 2 to the 8th is a 1, 2 to the 7th is 0, 2 to the 6th is 1, 2 to the 5th is 1, 2 to the 4th is 0, 2 to the 3rd is 1, 2 squared is 0, and 2 to the 1 is 1, and 2 to the 0 is 1. And that is the correct answer. Same as we got before. Okay, you could do the conversion with the math in the new radix. I've shown it here, showing the math in base 5. I don't like doing the math in base 5, so I'll just leave it there for your, in case you want to do something and you're really bored. Okay, you can also do other repeated division with the math in the other radix. Feel free to give it a shot. But if instead of going, say, from base 5 to base 3, instead of doing your math in either radix 5 or radix 3 or something unpleasant, it's easier just to convert to base 10 in between. So then you could just convert whatever you have from the old base to base 10 using direct evaluation or Horner's method. I usually use direct evaluation. And then take your value that you got in base 10 and convert it using guessing or multiplication into your new base. So, for example, here it is all just written out. If we want to go from 210 base 3 into base 5, if we first convert into base 10, okay, and it just happens that it's 21 base 10. That's a coincidence that the digits look alike. Okay, and then we take our 21 and we subtract off powers of 5 to figure out the new answer. Of course, if you had, we're going from 8 to 16, you would go through base 2 instead. You could go through base 10, it's just a little more work. Now, I just wanted to mention quickly that you can represent things other than numbers using binary, and you probably are familiar with extended ASCII code. Here I've actually shown you ASCII, a 7-bit ASCII code, which is the first code that was used. And you can see here we have all these teletype functions as well. I wanted to show you this because it's a form of a table you might not see very often, but I want you to know how to read it. So if we want to look at, say, the letter A, the top is the bit position 6, 5, and 4. So that would be 1, 0, 0. On the left, we would read the bit positions 3, 2, 1, 0, which is 0, 0, 0, 1. And that would be the representation of A using a 7-bit ASCII code. There's also, again, I mentioned before, an 8-bit extended ASCII code, and there's a lesser used 8-bit code called EBCDIC, EBCDIC, which was used by IBM. Thank you for watching. See you next time.